Hi, I'm Devin Guillory from Etsy, and I'll be presenting our ensemble-based approach to click-through rate prediction for promoted listings. So first, I guess I want to talk about the things I'll be talking about in this talk. One, I'll be giving a brief overview of Etsy's promoted listing product. We'll also be talking about the system architecture and pipeline. Next, we'll also talk about effective predicting algorithms and modeling techniques, which we use for this problem. And last, we'll discuss correlations between offline experiments and online performance. So some background, what is Etsy? Etsy is a global marketplace for unique goods. So we have a community of around 2 million sellers which sell handmade or vintage items as well as craft supplies. These sellers currently have greater than 45 million products active on Etsy, and we currently have over 30 million active buyers. So the promoted listing product is a product to help our sellers get their listings in front of an active audience, in front of people who may potentially want to purchase their items. So what we do is we actually blend our promoted listing results with organic search results for related queries and offer them a higher priority on the page. So how does promoted listing work at Etsy? In general, so sellers specify an overall budget for promoted listings. In general, we don't allow them to set individual bid pricing. Optionally, they may set a max bid per listing, but when it comes to the actual bid estimate, this is something that we predict and produce for them. Sellers also cannot choose which queries to bid on. This is something that's determined by our click-through rate and prediction algorithms, so it behooves us to put the correct listings in the right context for our sellers. We operate on a cost per click model, and the cost per click is determined by generalized second price auction. And in general, our score for ads ranking is a combination of the bid price as well as the expected click-through rate for a particular listing. This is a brief example of the second price auction model. We have the bid price and the expected CTR. It computes a score. In general, the cost per click will be based on the score of the previously ranked item divided by the score of the current item times the bid. So click-through rate prediction overview. So for our system for click-through rate prediction, there's three main components. One is the data collection, featurization piece. The next is the model training, and last is prediction. And I'll talk about each of these in turn. So for data collection, so what we do is we take training data over 30 days based on our logs, our aggregate visit logs. We treat negative examples as impressions that weren't clicked, positive examples as ones that were clicked. Due to large class imbalance, we actually do balanced sampling for our training. And we follow a progressive validation framework. So we evaluate on the following day to measure the effectiveness of our models. All of this is done in Hadoop. Yeah. So for model training, so we model the click-through rate prediction task as logistic regression, specifically on what algorithms we use to optimize and learn the weights for this. We use follow the regularized leader proximal algorithm. It's approximately the same thing as online stochastic gradient descent with L1 regularization. We do this, it's been proven to have success in the field, as well as it leads to very sparse models, which can effectively be used in other parts of our pipeline. We do our training on single boxes via Vopal Event. So for inference, our inference pipeline, so we pull the data from HDFS into a single machine for our training, and afterwards we package and ship the model back to a shared data store. From there, we have a system called UIE, which we deploy these packaged lightweight models to a bunch of smaller machines, which hide behind a virtual IP address. So we can then send either batch or real-time queries to this API or this service, and it returns the predictions. So I mentioned before, we do balanced sampling in order to train our models. So we need to calibrate the predictions in order to fit the correct distribution of expected click-through rates. I guess there's two components to it. In practice, due to the way that the click-through rates factor in with the bid and other components of our overall algorithm, what we do is we fit the distribution to previous day's distribution of predictions in order to calculate certain things such as log likelihood and stuff. We employ Platt scaling for our offline evaluation. So for evaluation, again, like I said, we train over T minus 32 days to T minus 2 days, and we evaluate the model over yesterday's data. The key metrics which we look for in this case is area under curve, log loss, and normalized log loss. Normalized log loss to account for the large class imbalance that I mentioned earlier. And the metric which we care most about in this case is actually area under curve. This was determined through a lot of evaluation, both of performance over time as well as performance throughout multiple experiments. So one thing we're doing, I'm visualizing here, is tracking area under curve over time and click-through rate over time as well to identify trends in the deltas of over days. The other thing is through multiple experiments, we've been able to establish AUC as our target metric due to both sign correlation, so improvements one way or the other in our area under curve and offline metrics is correlated to positive or negative wins on online experiments. And we also get scale performance, so single-digit improvements in AUC have corresponded to single-digit improvements in click-through rate. Okay, so now I'm going to talk about the specific model, which we go into in this paper. So for featurization, we categorize featurization according to two things. One are historical features. So historical features are based on how users have interacted with these promoted listings in the past. So this is whether they clicked or added to cart or led to a purchase and stuff like that. The other thing we have are content-based features. So these are features which are specifically based on the listing information, so information presented on the listing page. So for historical features, the type of things that we look at are impressions, clicks, cart ads, and then we apply some transformations to these features as well. For instance, for impressions, we do log scaling. We take the floor of the log of the impression count. And for click-through rate, we actually perform smoothing over the click-through rate. So by fitting it to a beta distribution, we're able to reduce variance in click-through rate, which is very useful for things that don't have a tremendous amount of examples. The next thing we have are contextual features. So these are things that are independent of user interactions. Some of these things are globally unique identifiers, such as listing ID, shop ID, categorical ID. Other things that we have are text features. These come from titles, tags, descriptions. We also have things such as price and currency code, which are numerical features. And last, we have image features. So for this, we're extracting, we're doing a transfer learning approach. So applying a pre-trained convolutional neural network, in this case, ResNet 101, over the images, over the primary image of our ad, and extracting the penultimate layer to get the feature vector. This corresponds to 2048 features. In order to combine all of these, we simply concatenate the features together. Yes. Yes. So it's a contextual feature. It's a dense feature vector. So it's a vector. Yeah, it's an embedding. Yeah. Yeah. Okay, next, models and performance. So first I'll talk about some data exploration that we did and insights that we got from it. So one of the things we did was independently look at how these various features are performing. Historical features, we noticed perform the highest for frequently occurring listings. On the flip side, we noticed that contextual features perform the highest for rarely presented listings. So one of the main questions we attempted to answer is how can we effectively leverage this information to create a valid model. So one of the things that we proposed is data splitting. And so I'll use the terms warm and cold here, and I'll use it throughout the presentation. So what we did was we split the training data into two cohorts. One for listings that appeared over n times in our training data, the other for listings that appeared under n times in this training data. For us, we set this in at 30, roughly corresponds to 1 impression per day for our particular training set. And then we trained separate models on each of these cohorts, the warm and the cold cohort. And then the goal is to figure a way to ensemble these predictions together in order to get the best possible predictions. So this is a brief visualization of how our models are trained. So we have an instance which is generated in Hadoop, and it contains our historical features as well as our contextual features. So during training, you can actually visualize it as a switch on whether or not it's occurred over n times. If it has, it goes to the historical model, and the historical model is only leveraging the historical features in this case. If not, it goes to the contextual model. So what exactly are these models? So for the historical model, we actually simplified the problem a bit and only used smooth CTR, and it turned to be a very effective model for predicting over the high frequency features. And for the contextual model, we ended up using title, tags, images, IDs and price features. So we also use various n-gram and prefix and suffix over the textual features. And this is trained over the low frequency data. So for the ensemble layer, initially the approach was a traditional stacking approach in which it's fed to both of these primary models, and then it's fed to an ensemble model and learned over that. But in this specific case, the high frequency model tended to dominate the contextual model, and we weren't seeing the intended benefits that we desired. So we actually set up basically a pass-through feature. For this is the impression count feature to enable our ensemble model to learn when to pay greater attention to historical or the contextual model, and it ended up improving performance. So to the results. So I'll speak primarily on the top row here, which is the area under curve, to explain the results briefly. Mixed corresponds to the entire test set. Warm, again, corresponds to frequently occurring, and cold corresponds to non-frequently occurring. All of these are trained over a simple baseline, which is a model trained strictly off of listing IDs, and it shows the corresponding performance. So as you can see here, the content-based model performs significantly better on the cold data than the historical model, and it actually performs worse than the baseline on the full data set. If we look at the historical model, it performs better on the mixed. It still outperforms the baseline on cold, but not to the extent of the content-based model. Once we go to the actual ensemble model, we get superior performance over both of the models for all of the different data splits. And we see the same performance lifts over log likelihood and normalized cross entropy. And so that's it with the presentation. I'll open it for any questions.